Hello and welcome back. You know, quantum computing, it's fascinating to watch it evolve, right? From just an idea to now where it feels like we're on the verge of something really big. Like it could actually start to tackle some of those really hard real world problems that we've been struggling with. And not like it's going to replace everything we use now, but rather like it'll work with our current tech, kind of a partnership.
Yeah, absolutely.
Yeah.
It's not about replacing everything. It's more about, synergy, working together, classical and quantum. Because there's certain types of problems, really computationally intensive ones that just overwhelm even our most powerful computers today. But a quantum computer, it can be built to just, blow through those.
Yeah.
And that's what we want to really dive into today. There's this recent article that digs into just how far quantum computing has come and what's possible, in the near future. And we want to break that down for you without getting too stuck in all the super technical stuff.
Perfect. Okay, so let's start right at the beginning. What is it about a quantum computer that makes it so different from the computer I'm using to record this right now?
Well, think about it this way. Your computer, all computers really, they use bits. They're like tiny switches, on or off, 1 or 0, right?
Yeah, okay.
But now imagine a switch that could be, let's say, both on and off at the same time. That's kind of the basic idea behind a qubit, the building block of a quantum computer. They can exist in this state we call superposition, kind of like, a coin spinning in the air.
Oh, okay.
Until it lands, it's not heads or tails, it's both. And that's just the start. We also have this thing called interference. Imagine like waves in the ocean. They can, crash into each other and get bigger, or they can cancel each other out. In a quantum computer, we actually use interference to sort of steer the computation towards the right answer. And then there's entanglement. Now, this is where things get really weird.
Okay.
It's like you take two of these qubits and you link them together in this spooky way.
Spooky.
Yeah, spooky is a good word. So once they're entangled, no matter how far apart you separate them, if you know the state of one, you instantly know the state of the other. And that's just not something you can do with regular bits.
So it's like they're connected, even if they're miles apart. That's wild.
Exactly, yeah. And all of these things, they give quantum computers this totally different way of handling information compared to classical computers.
So with all that, what kind of problems can quantum computers tackle that just wouldn't even be possible with a classical computer?
Well, take something like, let's say, predicting how a chemical reaction will unfold. You've got even a small molecule, it's got tons of electrons whizzing around, all interacting.
Right.
Trying to model that precisely on a classical computer, it would take forever, literally.
Right.
But a quantum computer, it's naturally suited to model these kinds of, quantum systems. And this has implications for, designing new drugs, new materials, really huge possibilities. Or think about optimizing something super complex, like a power grid. Balancing supply and demand, all the variables, it's mind-boggling.
Yeah, and it has to happen all the time, super fast.
Exactly. And those types of problems, the kind where classical algorithms get bogged down, those are the ones where quantum computers could really shine.
But like we talked about earlier, it's not about replacing our laptops or anything, right? It's more like they'll work together.
Exactly. Classical computers are great at, everyday tasks, running your apps, your operating system, the sequential stuff. Quantum computers will probably work more like, specialized processors. They'll handle the really heavy lifting, the specific calculations that need that quantum power.
Okay. Now, there was this term in the article that I wanted to ask you about, quantum circuit. It sounds like, I don't know, the blueprint for how a quantum computer does its calculations.
Yeah, you're on the right track. Think of a quantum circuit like the instructions you give to a quantum processing unit, or a QPU. It's like a program that runs on your CPU, your central processing unit, in a regular computer. But instead of manipulating bits, it's manipulating qubits using these quantum operations.
Okay. So what are the steps in this quantum circuit, this quantum program? How does it actually work?
So first, you got to take the problem you want to solve and you encode it into the state of the qubits, setting them up. And then you apply a bunch of these carefully designed quantum operations.
Quantum operations, like...
Well, they're kind of like the quantum versions of logic gates, but they use these special properties we talked about earlier, like superposition and entanglement. And these operations, they transform the states of the qubits. And finally, you got to measure the qubits. And that's when the magic happens. Measuring them forces them to collapse from that fuzzy superposition state into a definite 0 or 1, just like the spinning coin finally landing.
Oh, I see. So we go from this kind of blurry quantum world back to something we can understand, like ones and zeros. That's interesting. But the article also mentioned something about quantum circuits being probabilistic. What does that mean exactly?
Right, so that's a big difference between quantum and classical computing. If you run the same program on a regular computer, you get the same answer every time, right? But with a quantum computer, even if you run the exact same quantum circuit multiple times, you might get different results, like, flipping a bunch of weighted coins. You get a bunch of different combinations of heads and tails.
So you're saying there's no guarantee you'll get the same answer every time?
Not necessarily, no.
Hmm.
And that's because of the inherent randomness in quantum mechanics. So a lot of times, you need to run the circuit many, many times and look at the distribution of the answers.
Like, see which answer pops up most often.
Exactly. And that gives you a statistically reliable picture of what's going on.
So it's more about seeing the possibilities than getting one definitive answer. Fascinating. Okay, now, the article mentions some challenges that are holding back quantum computers. Things like circuit width and depth. What do those even mean?
Those are really important limitations, yeah. Circuit width, that's just how many qubits you have to work with. The more qubits, the more complex the problems you can tackle, generally.
Hmm.
But then there's circuit depth, and that's basically how many operations you can do on those qubits before you start losing the information they hold. It's like, that spinning coin again. You can only tap it so many times before it starts to wobble out of control and falls over.
Oh, okay, yeah. And that's because of noise and interference, right?
Right. It's called decoherence. And the deeper the circuit, the more steps in your calculation, the more susceptible it becomes to this noise.
So how are scientists dealing with that?
Well, there are a couple of main approaches. One is called quantum error correction. Basically, it's like spreading the information of one qubit across multiple physical qubits in a way that lets you detect and fix errors as they pop up.
So like building in redundancy?
Exactly. But it's really, really hard to do. And then there's also just improving the hardware itself, making qubits that are more stable, that can hold on to that quantum information for longer.
Okay, I see. And what about this error mitigation the article mentioned? How is that different from error correction?
So error mitigation is more about, minimizing the impact of those errors after the computation is already run. It's not as perfect as error correction, but it's proving super useful, especially now that we're getting into what we call utility scale quantum computing.
Utility scale, what does that mean?
Well, it means we're talking about quantum computers with, over 100 qubits and the ability to run thousands of quantum operations. And these machines, they can already tackle problems, especially in chemistry, that are just way too complex for even the biggest, most powerful classical computers to handle. It's really exciting to see that happen.
That's amazing. But the article did say that some of the really big game-changing algorithms, like Shor's algorithm, they're not quite there yet, right? So,
You're right. Shor's algorithm, it's this incredible theoretical breakthrough, especially for breaking encryption. But the quantum computers we have today, they're just not big enough or stable enough to run it effectively. But that's okay, because there's still so much we can do with what we have. We're focused on what we call near-term value. Find problems in chemistry, finance, materials science, optimization, where quantum computers can give us an edge, even with their limitations.
so finding the areas where they can be helpful right now.
Okay. Now, the article really emphasized the importance of software. Why is that so important?
Yeah.
We keep talking about these incredible machines, but it sounds like the software is just as crucial.
Think about it. Even if you had the most powerful quantum computer in the world, without the right software, it's basically a very expensive paperweight.
Right. It needs instructions.
Exactly. And a lot of these really powerful quantum algorithms, they require running the circuit thousands, even millions of times to get a good result. Plus, most real-world problems, they're going to involve both quantum and classical computing. You need software that can take the problem, figure out what parts can be done on the quantum computer, send it over, get the results back, and keep going.
So it's like a bridge between the two worlds.
Yeah, exactly. And if that bridge is slow or clunky, well, the whole process gets bogged down.
That makes sense. So that's where these quantum software development kits, or SDKs, come in. Right. SDKs like IBM's Qiskit, Quantinuum's TKE, Google's Cirq, they're designed to make quantum computing easier to use. Give developers and scientists the tools they need. Programming languages, pre-built libraries, so they can focus on designing and running their algorithms without needing to be, quantum physics experts.
Like a simplified programming language.
Yeah, exactly. It abstracts away a lot of the really complicated details. And the article also mentioned benchmarks for these SDKs. Why are those important? Benchmarks are important because, well, just like with regular computers, you need a way to compare different software tools. See how fast they are, how accurate they are. So these benchmark circuits, they're like standardized tests. They let you see how different SDKs perform on different quantum computers. Like, for example, IBM has this open source project that uses benchmarks to compare Qiskit to other SDKs.
So it's like a competition to see which one's the best.
It's not really about competition. It's more about, driving innovation, seeing what works well, what needs improvement. And the article really emphasized the importance of openness and transparency in all of this.
Why is that?
Because if these SDKs are open source, more people can contribute, find bugs, suggest improvements. It's like a big community effort. And having the benchmark results be public, that helps everyone see how the field is progressing, what the strengths and weaknesses of different approaches are.
So it's about collaboration and making sure everyone benefits.
Exactly. And that brings us to another important concept: abstraction.
Yeah.
Just like, with regular software, you don't need to understand every single detail of how the hardware works to use a computer, right?
Right.
It's the same with quantum computing.
Yeah.
These SDKs, they need to hide a lot of the complexity so researchers can focus on their work, their drug discovery or material science, without getting bogged down in all the details of manipulating qubits.
And that leads to domain-specific libraries, right?
Exactly. So just like in classical computing, where you have specialized libraries for machine learning or statistical analysis, we're starting to see the same thing in quantum computing. Libraries specifically for, chemistry or finance or whatever field you're working in.
So you don't need to be a quantum expert to use quantum tools.
That's the goal.
Yeah.
In all of this, it's all working towards this ultimate goal of achieving quantum advantage.
Right. We've mentioned that a few times. Can you explain exactly what that means?
Quantum advantage. It's that point where a quantum computer can solve a problem much faster, more accurately, or more cheaply than even the best classical computers we have. It's not about quantum computers being better at everything, but rather being significantly better at specific things.
So like finding those niche areas where they can really shine.
Exactly. And the article really highlights that getting to that point, achieving useful quantum computing, it's a massive global effort.
Yeah.
It's not just physicists and engineers building the machines. It's computer scientists, mathematicians, and experts from all sorts of fields working together.
It's a whole ecosystem.
It is, and it's only by working together that we can unlock the full potential of this incredible technology.
So just to sum up everything we talked about today, it seems like quantum computing is moving really fast. And while there are still challenges to overcome, the progress in software, especially these SDKs and domain-specific libraries, is really exciting. It's making quantum computing more accessible and bring us closer to that goal of quantum advantage.
Absolutely. It's been fascinating to watch this field go from theory to reality, and the possibilities, they're just mind-blowing.
It really makes you think, what problems in our own fields or in the world in general could be completely transformed if we could harness the full power of quantum computing.
No doubt. It's a rapidly evolving field with the potential to change everything.
Well, that brings us to the end of our deep dive today. Thanks for joining us. And as always, please like, share, and subscribe to this channel.